Hi everyone. So today we're going to be discussing a question which involves the geometric interpretation of a system of equations. Now what does that mean? So many times in algebra, whenever we have like a system of equations, a lot of times it's very tedious to solve that using just algebraic manipulations. So what we do rather is try to use some sort of trigonometry or try to convert it into a problem of geometry, right? Something or a problem of trigonometry, something that is a little bit easier to deal with. Because this trigonometric ratio, they have some interesting properties which are very hard to see if treated from an algebraic standpoint. So this is going to be quite interesting, and yes, let's just see how this works out. So this is a question from the Math Olympiad Program, the MOP, in the year 2001. And the MOP is basically the American equivalent of the IMOTC that we have in India. So it's their camp basically for the IMO. And in this video, we're going to be looking at how we are going to solve a system of equations, and more importantly, solving the system of equations using a little bit of geometry and trigonometry, right? The geometrical interpretation of the algebraic question. Then we're also going to be looking at an interesting result, a very standard result, but it's good to keep in mind, and it's very helpful in a lot of these exams. Then we have book sessions for senior math Olympiads, and at the end, a similar challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so the goal is to find all real numbers, ABC, so they don't necessarily have to be integers, such that they satisfy the given system of equations. And they've really given me three equations over here. Now again, what I see is that I have some a squared, b squared, c squared terms in the first two equation, but in the third equation I really don't have that. Well, the degree is same because I have ab, but essentially I don't have any squared terms. So solving this algebraically can be quite tedious, and that's something I don't want to do. Secondly, what I notice is that this ab plus bc plus c is equal to 1. This is quite interesting, I can work with that. So maybe what I can do is I can plug in A is equal to cotangent alpha, B is equal to cotangent beta, and C is equal to cotangent gamma, right? And sooner or later, you're actually going to see why this was helpful and why I took this substitution in the first place. And I think we should be writing that we are taking alpha, comma, beta, comma, gamma belonging to 0 to pi, such that they satisfy these three conditions, right? And another thing to maybe look at is that the function f of x is equal to cotangent x. This is surjective, or it's onto. Now, what is an onto function? So, for example, if I write, let's say, y is equal to cotangent x, that means that for every y in its range, there exists an x in its domain, so that y is equal to cotangent x. And that's really important because when I write this a is equal to cotangent alpha, how do I know if there exists an a corresponding to that particular alpha? There does exist because we know that the cotangent function is surjective, right? Surjective. Cotangent is surjective. We know that the cotangent is surjective, and therefore such an a exists, so that a is equal to cotangent alpha. That is why I'm able to use the substitution, otherwise I cannot. And why is it surjective? Well, I think you can pretty much get it from the graph. I'll just make it over here. So we have this point 0. We will obviously have something over pi by 2 and over pi. Now, as you might be knowing, we have a vertical asymptote at pi because the cotangent function is nothing but cosine over sine. And sine pi is 0. So anything divided by 0 will be non-defined, and therefore you will have something sort of a vertical asymptote over here. So this graph essentially would look something like this. Yeah, and this would go on till infinity in a way. Okay, that's like a very rough graph, but anyways, I think you get the point. So moving on to the actual part of the solution. So just to remind, we have used this substitution. A is equal to cotangent alpha, B is equal to cotangent beta, and C is equal to cotangent gamma. And maybe let's just label these three equations as 1, 2, and 3 respectively. So if I use the substitution into equation 3, right, So if I just maybe use this substitution in equation 3, I'll get cotangent alpha, cotangent beta, plus cotangent beta, cotangent gamma, plus cotangent alpha times cotangent gamma. All of this is equal to 1. And now what I can do is I can maybe just take cotangent gamma common and I can just factorize it a little bit. So I'll get cot alpha plus cot beta is equal to 1 minus cot alpha cot beta. So you can see some interesting things forming over here. So I can write cotangent gamma as 1 minus cotangent alpha cotangent beta divided by cotangent alpha plus cotangent beta. And I think here I'll just maybe kind of remind you of an interesting property that we have in trigonometry. We know that the cotangent alpha plus beta, right, a property or this property is often ignored because we usually remember tan alpha plus beta, but cot alpha plus beta is also worth remembering, right? So cot alpha plus beta it so happens to be cotangent alpha cotangent beta minus 1 divided by cotangent alpha plus cotangent beta, right? Which is quite similar to what we obtained over here, right? Which I wrote in purple. And the only difference is that the numerator needs to be shifted by a negative sign. So I can write negative cotangent gamma is equal to cotangent alpha cotangent beta minus 1 divided by cotangent alpha plus cotangent beta. Now from the allied angle formula, I know that cotangent of 180 minus gamma, right, cotangent pi minus gamma is negative cotangent gamma. So this essentially becomes cotangent of 180 minus gamma is equal to cotangent of alpha plus beta, which is excellent because 180 minus gamma then becomes alpha plus beta. So that implies that alpha plus beta plus gamma is 180 degree. Remember, alpha, beta and gamma were angles, right? So obviously they sum up to 180 degree as we have proved over here. So therefore alpha comma beta comma gamma are angles of a triangle. They're angles of a triangle. And I think that is a pretty interesting result, right? That's a pretty interesting result on observation, whatever you call it. So if we have cotangent alpha, cotangent beta, plus cotangent beta, cotangent gamma, plus cotangent gamma, cotangent alpha is equal to 1, then that necessarily implies that alpha plus beta plus gamma is equal to 180 degree and vice versa. That you can go the reverse, you can go in the reverse direction as well. In other words, you can just say that alpha comma beta are angles of a triangle because they satisfy the angle sum property. Okay, I think that should be pretty clear. So moving on, what does that mean? So essentially, I can like maybe draw this kind of a triangle over here with the angles alpha, beta, gamma, and the sum up to 180. Now the side opposite to alpha, I can take it as capital A, side opposite to beta will be capital B, and side opposite to gamma is capital C. Now let me just maybe remind you what the original equations were. Well, we had A, right? A was cotangent alpha, B was cotangent beta, and C was cotangent gamma. So our goal is to find ABC. And if we find alpha, comma, beta, comma, gamma, we can eventually find ABC. Now, if you look at equation number 1, which I had marked up top, it was A square minus 2B square is equal to 1. Or I can write A square is equal to 2B square plus 1. A square is cotangent square alpha is equal to twice of cotangent square beta plus 1. And I can just add 1 on both sides, right? I can just add 1 on both sides. And why I do that? Because cotangent square theta plus 1 is cosecant square theta. So this becomes cosecant square alpha. This becomes 2 times cotangent square beta plus 1. So effectively, cosecant square alpha becomes twice of cosecant square beta. And let me label that as equation number 4. Similarly, we had equation number 1 as this, right? This was what? Equation number 1. Then we also had 2b square minus 3c square is equal to 1. That was equation number 2. If I can just maybe add 1 and 2. If I add 1 and 2, what do I get? A square minus 3c square is equal to 2. And kind of using the similar idea, cotangent square alpha so happens to be 3 times cotangent square gamma plus 2. Again, just add 1 on both sides. So you'll get cosecant square alpha is equal to 3 times cotangent square gamma plus 1. Because I added 1 on both sides, so you get 3 on the right hand side, which can be factorized. So it so happens that the cosecant square alpha is equal to 3 times cosecant square gamma. right? And this is equation number 5, I believe. Yep. So what result do I have? So from equation number 4, I know that cosecant square alpha is equal to twice of cosecant square beta. Or in other words, 1 by sine square alpha is equal to 2 by sine square beta. And if I just maybe convert this into sine and just sine without the square terms, I can just write that root 2 times sine alpha is equal to sine beta. Similarly, from equation number 5, I can directly write that root 3 times sine alpha will be equal to sine gamma, just by using the same logic. And let me just label this as equations 6 and 7 correspondingly. So what does that mean? That essentially means that 1 by sine alpha is equal to root 2 by sine beta is equal to root 3 by sine gamma. Right? Just kind of like rearranging the terms, which is equal to some quantity k. Right? Does this remind you of something? What were alpha, beta and gamma? They were angles of a triangle. Right? Alpha, beta and gamma, they were angles of a triangle. And in any triangle, you have a over sine alpha is equal to b over sine beta is equal to c over sine gamma. What does this mean over here? Do you actually notice the resemblance of the sine rule to equation number 8? Equation number 8 is basically the sine rule. A over sine alpha, b over sine beta, c over sine gamma is equal to k. The only difference is that sine rule is talking about the ratios of the sides. Right? So the side A will be A, the side B will be root 2 times A, and similarly the side C will be root 3 times A. They will not be 1, root 2 and root 3. They can if A is equal to 1, but that's not a necessary condition. So I know the angles alpha, beta, gamma, or I at least know them as variables. I know the sides as a ratio. A is equal to A, B is equal to root 2A, and C is equal to root 3A. What next? Next is again a very critical observation. Is that A squared plus B squared is actually C squared. Why? Because A squared is nothing but A, B squared is 2A squared, and C squared so happens to be 3A squared. Right? So we have a right angle triangle. A, B, C are Pythagorean triplets in a way. Right? A, B, C satisfy the Pythagorean property. So they are Pythagorean triplets. In other words, we have a right angle triangle basically with the sides A, B and C. Now, which is the right angle? The angle opposite to hypotenuse, which is C, will be a right angle. And what's the angle opposite to C? It is obviously gamma. Right? So this is gamma, which so happens to be 90 degrees. This is C. And then you can really choose whatever you want for A and B arbitrarily. So this becomes A, this becomes B. Just to remind you, the convention that I'm following is the angle opposite to alpha is A and angle opposite to beta is B. So gamma is 90 degrees. What was gamma? I had done the substitution C is equal to cotangent gamma. So C is equal to cosine 90, right? Divided by sine 90, and cosine 90 is 0, sine 90 is 1. So C becomes 0 by 1, which is 0. And that is excellent because now I'm basically done with the question. So we have gotten that C is equal to 0 and 2b squared minus 3c squared is equal to 1, which is equation number 2 in our original question. Equation number 2, right? So if I just plug in maybe c is equal to 0 over here, I'll get 2b squared is equal to 1, or rather b is equal to plus or minus 1 by root 2. So I've got a set of values for b as well. Now I have a square minus 2b square is equal to 1, which was my equation number 1. And 2b squared so happens to be 1. So a square minus 1 is equal to 1. Or in other words, a square is equal to 2. Therefore, a is equal to plus or minus root 2. So what have we kind of received till now? We know that c is equal to 0. B can be plus or minus 1 by root 2. And a can be plus or minus root 2. But we essentially need to write the ordered pairs a comma b comma c. So we need to know, for example, if we have root 2 as a, correspondingly, do we have root 1 by root 2 as b, or do we have negative 1 by root 2 as b? So what's the kind of the parity relationship between a and b? And to figure that out, we use a third equation. AB plus BC plus AC is equal to 1. So you effectively just plug in C is equal to 0 over here, and you'll get AB is equal to 1. Therefore, A comma B have the same parity, or they have the same sign. Effectively, the product is a positive quantity, so they both need to be positive or they both need to be negative. So the solution set of A comma B comma C can be written like this. We have root 2 comma 1 by root 2 comma 0. This is one solution. And the second would obviously be the negative of this. Negative root 2, negative 1 by root 2, and 0. So these are the two solutions, and these are the only two solutions. So yes, I hope that was quite an interesting interpretation of this question. And you really kind of saw that using that smart kind of geometric substitution that we used, trigonometric substitution in the beginning, we actually kind of reduced this problem down to something that was very simple. And coming back to like what was the intuition of the substitution, why I did this? Well, I kind of knew that this result holds. This result that I marked over here, I did know about it, that if cotangent alpha, cotangent beta plus all of these quantities is equal to 1, then alpha plus beta plus gamma is 180 degree. It's something quite interesting, can be very easily ignored, but like you've seen over here, it can prove to be quite critical. And therefore, when I saw this AB plus BC plus C is 1, I kind of like got in my mind that we can use cotangent substitution and then transform this into trigonometric, kind of like a trigonometric question rather than algebraic question, in which we will have a triangle with the angles alpha, beta, gamma. And I think that's probably the intuition for the substitution over here. But anyways, I hope you learned something from that, and let's move forward. Okay, so you have some book suggestions for National Math Olympiads. Elementary Number Theory by David Burton, Problem Solving Strategies by Arthur and Gell, Functional Equations by Venkatachala, Problems in Plane Geometry by Sharigan, Elementary Number Theory by Sierpinski, Graph Theory by Harari, and Combinatorics by Brualdi. So we have a similar but challenging problem. I don't know if this is challenging, but it's very similar at least, and it uses a substitution, a trigonometric substitution, but it's probably a little bit easier to see, and I most likely think that you have seen this before, because this is an IOQM problem, right? And again, like we have a system of equation, right? X square plus y square 49, y square plus yz plus z square is 36, and x square plus z square plus xz root 3 is 25, and then find out the value of this quantity. If it can be written as p root q, find p plus q. I believe this came in IOQM, and so after seeing this video, try and maybe like make certain substitutions using trigonometry, and yeah, let's see how that goes. And of course, I'll see you in the next video. Till then, thank you very much, and bye-bye.
Cheenta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.